Okay, let's look at some of the approximations for the dispersion relation for short and long waves and some of the behavior that goes along with the two limiting cases. So short waves are waves where we have L over D being less than 2. Long waves, we have wavelength divided by depth is greater than 20. In terms of the parameter KD, which is what the hyperbolic tangent cares about in the dispersion relation, we have KD is going to be large for short waves, and similarly for long waves, KD will be small. Okay, that's just converting L over D to KD. Okay, all right, so let's look at the limits of the hyperbolic function. Okay, that's really the beauty of this classification here. So hyperbolic tangent of KD when KD is large, hyperbolic tangent goes to 1 actually. And for long waves when KD is small, hyperbolic tangent of KD actually just goes to the argument itself, KD. Regardless if you're short or long wave or intermediate, you can always just plug it into tangent of KD, right? Now the full dispersion relation is omega squared is equal to GK hyperbolic tangent of KD. And let's look at how that simplifies for short and long waves. So for short waves, we have that omega squared is equal to, we'll plug in the 1 for hyperbolic tangent of KD. We just get GK times 1. We'll just leave it out, okay? Long waves, this hyperbolic tangent of KD is going to go to KD itself, and we have omega squared is equal to GK squared times D, okay? Those are the two limiting cases. Now if we look at the phase speed of the wave, remember that it's always given by L over T, but remember that L over T can also be rewritten as omega and K, omega over K, if you just convert those two variables, okay? So if we do that, we can take the dispersion relation, divide both sides by K squared, and then take the square root, in which case for short waves, we would get that the phase speed is equal to G over K, quantity square rooted, okay? All waves, is going to be just omega squared divided by K squared square rooted, in which case C is equal to the square root of G over K times the hyperbolic tangent of KD. And for long waves, if we insert that approximation, divide both sides by K squared, we can see pretty easily that it goes to a formula that we've seen in other classes involving fluid mechanics, which is the square root of G times the depth, okay? So really that's the long wave speed. If you see somebody telling you that's the wave speed, they're talking about long waves, okay? So what are the consequences of these formula? What are they really kind of telling us? Well, for short waves, if we look at this wave phase speed, it depends on the wave number, which is the wavelength, which is the period of the wave, okay? And what that means is that in deep water, waves of different periods travel at different speeds, and the adjective that we use for that is that they are dispersive, okay? So deep water waves are dispersive, and that's really the meaning of that word dispersion. Deep water waves are dispersive, meaning that different periods travel at different speeds. Okay. For the general case, we have, just the general case. For long waves, we see that the wave speed is independent of the wave period, provided that the waves are all long, right? So what that means is that the depth sets the speed of the wave, okay? So depth sets the speed. And then all waves that are shallow in a given depth travel at same speed, right? So waves are not dispersive, actually, if they're all shallow. Waves are not dispersive. So a couple of examples for those two limiting cases. Let's see if I can get rid of this. So good examples of short waves are wind waves. So wind waves in the middle of the ocean. So wind waves at sea. So you're in the middle of the ocean. Maybe it's a mile deep. The wavelength is 20 meters. And even if you have different wavelength waves, they're all going to be short waves relative to the depth, and they're all going to be passing through one another. Okay, so that's a good example of a short wave. A good example of a long wave is a tsunami. Okay, so a tsunami is a good example of a long wave. Sometimes when you're at the beach and you see all of the waves kind of lining up to break one after the other, that's another good example of long waves. If the waves are truly long in shallower water near the shore, none of the waves are going to be passing each other because they're not dispersive. They're all traveling at the square root of GD, which means that one wave after the other will just proceed toward the shore where they're breaking. Okay, those are a couple of good examples of short and long waves. But really, one of the main reasons that we classify them is because of this limiting behavior of the dispersion relation, short waves and long waves, and you can sort of understand the behavior of waves in the limiting cases. And if you know that your particular wave fits into one of those or the other, then it makes it easier to understand the physics. The other thing to think about with short waves is that short waves, if they are truly short, they really have no knowledge that the bottom is there. Notice that the wave speed has no dependence on the water depth for a truly short wave. And so a short wave will just cruise over the ocean bottom. You know, it could be relatively shallow water, but if it's deep in sort of a relative sense, those waves are just going to keep going in the same direction they're going, and they're not going to be modified at all by the underwater bathymetry. Okay, so that's another sort of consequence of short waves, is that they're unaffected by bathymetry. You might want to add that one to this box over here. Okay, and I think that's it.